All right, here we go. So for number 20, okay, we're going to need 4 objects. The 4 objects are going to be a 2-liter will represent one of the charges. Mario ball will be one of the charges. Oven mitt will be one of the charges. And the giant slinky. And initially in number 20, do you have it pulled up? Yeah, all right. So initially in number 20, these are going to be infinitely far away from each other, okay? So I'm just going to put them somewhere else in the room. If anybody's watching this, they're just off camera, okay? And I'll be bringing them in one at a time. The place we're going to line them up, oh, is this anybody's notebook? Is anybody's notebook? No? Okay, it's been here for a while. Okay. The place we're going to line them up, okay, is here. So I'm going to be bringing them from infinitely far away. When I say infinitely far away, it means that they cannot interact with each other. So they're so far away that they're not exerting any forces on them, and we're going to bring them in one at a time. And that's the key for any time you're trying to find the stored energy in a system of charges. Pretend they're infinitely far apart, even if they don't tell you that, and then bring them in one at a time. Okay, so I'm just going to put these somewhere else in the room. Here's going to be the infinitely far apart. We'll put one over here, we'll put one here, we'll put one here, and here. They're so far away from each other that they're not interacting. Let me move this mic down a little bit, otherwise I'm probably spiking on the volume levels. Okay, all right. Yeah, I should take this off. All right, here we go. And I believe there were 4 identical point charges. Let me just confirm that real quick. So this is number 20, chapter 19. And they are 4 identical charges plus 2 microcoulombs each. Brought in from infinity and fixed to a straight line, and they're located 0.4 meters apart. And we're supposed to determine the electric potential energy of this group once they're all together, okay? So I'm going to go ahead, and I'll make a new thing here in OneNote, okay? You're not doing conversions, obviously, okay? All right, here we go. So we'll add a page. I'll title it later, okay? But we're going to bring in the first charge, okay? And if you're working on something else because you're good on this problem, that's fine, but you need to do it quietly. Yes? Some nods? Okay, all right. So we're going to bring the first one in. Oh, we don't want it to be green, though. Hold on just a second. I was showing where point totals were for physics conversions. There we go. All right, let's get rid of the green. All right, so to bring the first charge in, think about it. If everything is infinitely far away, what was the potential at this point before I bring this charge in? It's just going to be 0. All right, so there's no hill or ditch in the ocean, okay, that we have to push uphill. It's not going to fly in on its own. Yep, okay. All right, are you okay if you sneak this way, just stay low kind of thing? Yeah, there we go. Perfect. Awesome. That is great. I love it. Okay, all right. Okay. So this first one that we bring in, okay, it's not going to go downhill. It's not going to go uphill. It's just like there's nothing, okay? Or another way of thinking about it is we don't have to do any work to bring it to this location, okay? It'll just move there freely. There's nothing helping, pulling on it, and there's nothing fighting against us. Is that okay? All right, so we're going to bring the first one in, and the potential at that spot we're bringing it into right now is 0, okay? Pardon me. All right, so I don't have to do any work to bring this in. So I don't have to do any work, okay, or there's no work done on it by a field or anything. Then when we get to this spot, okay, the stored energy is just 0. Another way to think about it is if I let go of this, is it going to want to fly apart at all or fly towards anything? No, it's just going to stay put. So there's no stored energy there. Is that okay that there's no stored energy? All right. So to bring in the first charge, no stored energy, okay, or my change in EPE is just 0, okay? So for this first one, okay, my change in EPE is just 0, okay? Now, that's for the first one. Now, for the next one, I'm going to bring it in and put it at a location next to it right here. And this one's not going to come in for free. In fact, if these are another positive charge, they're going to repel each other. So I have to do work to bring it in. Is that okay? So if I'm doing work to bring it in, it's like me sort of like me squeezing a spring, right? Some stored energy is going to go up. Is that okay? All right, I'm going to kick the door shut before I forget. And we got somebody out there. I'll make it so they can. There we go. All right. And if we want to figure out how much work or what my change in energy is going to be or the energy associated with bringing that in, I need to know the potential at this location. So I'm going to go ahead and do that in the first part here, okay? Oh, and instead of having like tons and tons of subscripts here, I'm just going to draw a line, okay, and like treat it like a new problem every single time. So I'm not going to write V1, V2, V3, V4, EP1, EP2. I'm just going to be like, this is like the potential at this point, and then we'll do like different, like all new problems every time. Is that okay? All right, so I'm gonna play a little fast and loose with my subscripts. So what's the potential at that point? Well, it'll just be KQ over R, where this distance R was given in the problem as, got my book in the wrong spot here. This distance r was given as something. 0.4 meters, thank you, okay? So we know the 0.4 meters, and we also know the charge is 2 microcoulombs. So 2 times 10 to the minus 6 coulombs. So I know, thank you, so I know Q, I know R, I know K. Is that all right? So I can find the potential at this location, okay? We don't need that yet, but we'll need it for bringing in the next charge. So now I'm going to bring in the second charge. So the configuration here has no stored energy. This next configuration, okay, I've got a positive charge. I'm going to bring in a positive charge to this location where I know the potential, okay, is KQ over R. And we'll figure out how much stored energy now, because there will be some stored energy. So let me go get an object. So I'll admit this time will have a positive charge. So as I bring this towards the 2 liter, okay, as I bring this towards the 2 liter, which has a positive charge, I've got to push on it. I've got to do some work on it, okay? It doesn't want to come in on its own or anything like that. I got to fight against it. So I'm putting that work is going to show up as stored energy in the system. Is that okay? All right. So I bring it into here and I put this location. So if I want to figure out how much work I did or my new stored energy, okay, now this is where we need to relate our electric potential energy to our potential at that point. Okay, so remember that the idea that EPE, I want to do this somewhere as an aside. Hold on just a second. Let me zoom out. I don't want to put it right there. I'm going to do this. Yeah, let's do this. Oops. No. There we go. Let's do this. Okay, so remember that EPE over Q equals V, or our change in EPE over Q equals our change in potential compared to infinitely far away. Is that okay? All right, so if I want to find out how much stored energy do I have now, okay, and I started at 0, okay, with this configuration, I can just take my V times my Q. Is that all right? Okay, so to get this new configuration compared to infinitely far away, I can get my stored energy is just going to be my V times Q. Is that okay? All right, so I can go ahead and do that. So I'll go ahead and say that the change in EPE here compared to when this charge was infinitely far away, okay, where I would say there's no stored energy at all in that configuration, okay, as I bring it in, is going to be whatever the potential is at that point times the charge that I bring in, okay. Now, the nice thing that they did here is all the charges are the same. But if they were different, okay, it would be whatever I got from this charge at this location, okay, that potential times whatever this second charge I brought in is. The only reason the key says stuff like KQ squared over R is because both charges are the same. It's really the potential at this spot times the charge that you bring in. They just happen to be the same. Is that okay? All right. Is everybody else okay with that? Because it's a very important point, because they won't always give you the same charges in the configuration, okay? All right. So what will this change in EPE be? It'll be, you know what? I am going to use numbers. I changed my mind, okay? Let's go ahead and call this V1, okay, just to denote this. It'll be my potential at 1 times, I'll go ahead and number them, Q1, Q2, times my Q2. Are you okay with that? Since I said all that anyway, let's go ahead and just number them. Okay. And now we can plug in. We know those are the same, so it'll end up being K, Q, Q kind of thing over R, or KQ squared, and that's what the key makes it look like. Is that all right? I'm going to go ahead and erase that, though, and I'm going to actually put in the numbers. Okay. So I'm going to have here that for this new configuration, I have stored energy compared to the nothing. In fact, I'm just going to put, we'll just put EPE because it's compared to nothing. We'll have V1, which is K times 2 times 10 to the negative 6 coulombs over R, which is 0.4 meters. That whole thing right there times the charge I bring in, which happens to also be 2 times, let's make this more legible, 10 to the negative 6, 2 times 10 to the negative 6 coulombs. Are you okay with the numbers going in there? And I didn't put K in. That's the 9 times 10 to the 9th that's on the equation sheet. You can just look that up. Is that okay? All right. So that would be how much energy is stored for just these two. But now I got to bring in 2 more. Okay. So where am I bringing in the third one? I'm bringing it in right here. Okay. So now we got to figure out the potential at that location. I'll just call that V2. Okay. And now we have 2 charges that are already here. So the potential at this next location right here is due to both of these. Is that okay? All right, so let's figure out what that is. Okay, so it'll be, let's raise this up. I'm just standing. Yep. So it'll be, I need a little more space. There we go. So our V2 will be K let's go ahead and put the numbers in. 2 times 10 to the negative 6 coulombs, okay, over one of these distance will be 0.4 meters. The other distance will be 0.8, just because of the setup where they said they're along a line. Are you okay with the two different R's here? Yep, okay, all right. And that's just based on the set of the problem. If this was like an equilateral triangle or something, you just do whatever is the physical setup of where they're going, where they're at, okay? So we'll have, this will be 0.4 meters plus, since they're both positive charges, 2 times 10 to the negative 6 coulombs for that other charge, okay? And it's 0.8 meters away. So we get that potential at 0.2 there. And now let's go ahead and bring in, clean this up a little bit. This was our little aside. Yep. Let's go ahead and bring in, okay, our next charge. Okay. So now from very infinitely far away, let's go grab Mario Ball this time. And he's a positive charge. So now when I bring him in, I'm going to have to do even more work than I did last time, because it's like I'm pushing him up an even bigger hill. Does that make sense? So I'm like pushing him up an even bigger hill, because now we have two mountains here. So I have to push him up even higher than it was for the first one. So now we have even more stored energy than we did before. Okay, but this is for just bringing this one in. So if I wanted to know how much stored energy do I have now, I'd have to add up the stored energy that I already had with the additional stored energy from bringing in the third one. We'll do that at the end because we need all four, but is that idea okay? So this is just the extra stored energy, or the change in EPE we have for bringing this guy in, okay? So let me go ahead and get that here. Whereas this one really was just the EPE of that new system. So for this one, I actually am going to go ahead and write the change in EPE for bringing the third one in here. Oh, let me get my picture. So we're going to have, we'll call this Q1, we'll have Q2, and now we have Q3. Oops, not Q2 again, Q3. All right, so we'll go ahead and say now our actual change in electric potential energy for this setup, okay, to bring that guy in was the potential at that spot, okay. I'm just going to write V2. It's whatever this works out to. Is that okay? All right, V2 times the charge that we brought in. And the charge that we brought in was, again, a 2 times 10 to the negative 6 Coulomb charge. Is that okay? All right, who has questions before I go any further? This is the change in electric potential energy to bring in the third charge. This is not the actual energy stored in a 3-charge system. It's the additional energy for bringing in the third charge. So it really is a delta compared to what we initially had. In the questions? You're still good? Yep. All right. Okay. You guys can ask questions. I just won't say your name. You're welcome to ask questions. Okay. All right. Because I don't think, have I ever recorded one for you guys? Have this has ever happened? No, because I've got so many. But there are apparently none for chapter 19. So this will be the first one, I think, for chapter 19. Okay. All right. So now before I go any further, I do need to know the potential at this fourth spot. I'm going to bring a charge in. I'll go ahead and just call that V3. I'll just call that V3. And the reason I need to know that is because as I bring in the third charge, I'm going to be bringing it up an even bigger hill kind of thing. So I'm going to do even more work. So I got to know what the potential is at that location. So we'll go ahead and write that V3 equals, and I need all these distances on here. Let me make the picture better. So this is from here to here is 0.4 meters. From here to here is 0.8 meters. And from here, where am I going to fit this in? From here all the way to here, getting a little messy, is 1.2 meters. Are you okay with all those distances? So now I'm going to do K this Q over this distance, plus K this Q over this distance, plus K this Q over this distance. Instead of writing Q1, Q2, Q3, I'm going to go ahead and put the charges in and write it out. Is that okay? All right. So it'll be K 2 times 10 to the negative 6 coulombs over, I'll just do the 1.2 meters first. Plus, these will all be pluses. And the reason they're all pluses is because these are all positive charges. Otherwise, I would either put the negative on here or I'd put the negative out front. Are you okay with that? If we had a negative charge in the mix, we'd have to account for that because that would make it, if I was bringing a positive charge and I had one of these are negative, I wouldn't be as high up. It wouldn't be going up as much of a hill. Is that okay? All right. Okay. Plus, this will be, let's do the 0.8 meters plus K 2 times 10 to the minus 6 coulombs over the 1.2, my bad, 0.4 meters. Are you okay with all those? Yep. All right. And then so finally, we bring in the fourth one, okay? So that's the giant slinky back there. All right. So we've got the slinky, okay? The giant slinky is our fourth positive charge, okay? I'm going to bring this in, okay? And as I bring this in, I have to do even more work because I'm going to an even higher spot than I was for any of the other ones, okay? So we're going to get a whole bunch more stored energy as a result of bringing this one in because I'm not just fighting against the first one. I'm fighting against the first one, the second one, and the third one. They're all trying to repel this. Is that okay? Yeah. All right, so I have to do a whole bunch of work to bring this in, okay? And I'm going to slide this over just so hopefully these all are appearing on the screen. There's a slinky somewhere over here. It's the fourth one. They're all lined up, okay, the four objects, okay? All right, and then so this extra change in electric potential energy as we bring the fourth one in, using this idea right here again, screen freaked out on me. Using this idea right here again, okay? We can figure out that change in EPE, okay, based on that change in potential compared to really far away to where we're bringing the positive charge to by just taking, make it look like the other one, yeah. So we're going to say our change in EPE here will just be our, oh, did I not section something off or did I delete something? Hold on just a second. We had V2 EPE. Nope, we're good. So this said the V at 1. I feel like something went wrong in my notation somewhere. I will double check here in a minute. But this should be equal to V3 times that charge that I bring in, which is 2 times 10 to the minus 6 coulombs. All right, let me double check here because I feel like I forgot something. So this one we bring in for free. There's our V1 times Q2, and then where did V2 go? Oh, here it is, yeah. V2 times that one, and then V3 times the charge you bring in. Is that okay? They are all up here. I briefly lost track of one of them, okay? All right, so now we'll have all these change in EPEs. So we'll have, the first one again was 0, but we'll have this one, we'll have this one right here that we brought in for the second one. We'll have this one right here that we brought in for the third one, okay? And then we'll have this one right here that we brought in for the fourth one. Okay, go ahead and draw a line there. That's why I couldn't see it. Okay, so this was for bringing in that fourth charge. Now, what do I have to do to all three of these numbers? The first one was 0. What do I have to do? Just add them up to get the total stored energy in the system. Okay, now because they called all of these Q the same charge, okay, you could have done some factoring out and simplification with the algebra, but they don't have to give you all the same charge on the test, which is why I have broken this up the way I have, so that you know how to deal with it if it's not all the same charge. Is that okay? Yeah. All right. Let me zoom out so we can see the whole thing. Where do you guys have questions? Okay, I'll call this box 1 up here, box 2, box 3, box 4, re-explain or questions. Oh, and in box 4 there, this is when we have all 4 charges now lined up, okay? And then we just add up all these numbers. All right, questions? Yep, go ahead.
So this was a pretty extensive problem. There doesn't seem to be many shortcuts. Is this probably a multiple choice problem?
No, this is with 4 charges. I would hope that this is free response. With 2 charges, I could see it being multiple choice because you bring the first charge in and that doesn't make you do anything at all, right? You do no work, literally and figuratively, right? You're just like 0, okay? And then the second charge, that's what problem we're also going to do today. Problem, this is 20, right? I think problem 13 is the other one we're going to do today, and that's just 2 charges. And you'll see that that is much, much, much quicker. The wrinkle on problem 13 is that one's a positive charge and one's a negative charge. So you don't have to fight to bring them in. They'll just fly in on their own. So instead of the energy going up, the energy is going to go down from when they're infinitely far away. Okay? But we'll get to that one in a little bit. We're going to do the circuits lecture, and then we'll come back to it. Yeah, I want to make sure we have time for the circuits lecture. Questions? I'm not recording that one either. Questions? Or re-explain? All right. At some point, if this goes to YouTube, I'll let you know, but this will be in your in OneNote if you need it. I'll label that later. Okay? All right, let me stop the recording here real quick. I say it'll be on YouTube. That assumes that I actually got audio and my battery didn't die and everything else, and that I remembered to hit record. I did remember to hit record, so at least we have that going for us.